Calculation of probability of failure on demand, PFD, as per ISA TR84.02, Part 5. The detailed methodology for calculating the probability of failure on demand, PFD, of logic solvers and safety instrumented systems is a crucial aspect of ensuring the reliability and safety of industrial processes. Below are the key steps and considerations for this calculation. 1. Understanding failure rates. Failure rate. The failure rate of each component involved in the SIS must be determined. This can include both the dangerous and safe failures. Dangerous undetected failures. Failures that do not get detected by diagnostic tests and can cause the SIS to fail on demand. Safe detected failures. Failures that are safely detected and do not lead to a system failure on demand. 2. Diagnostic coverage. Diagnostic coverage, DC. The effectiveness of diagnostics in detecting failures. It is expressed as a percentage and calculated based on the ratio of detected failures to the total failures. Proof testing. Proof test interval, TI. The time interval between manual tests that verify the SIS is functioning correctly. This interval greatly affects the PFD calculation. Proof test coverage. The effectiveness of proof tests in revealing undetected failures. 4. Mean time to restore. Mean time to restore. The average time taken to restore the SIS to its operational state after a failure has been detected. This includes repair time and any delay in initiating repairs. 5. PFD calculation. The average probability of failure on demand PFEG can be calculated by considering the dangerous undetected failure rate, the proof test interval, and the mean time to restore. 6. Redundancy and voting configurations. Redundancy, using multiple components to perform the same function to improve reliability. Voting configurations. Systems can be configured in various voting logics like 101, 102, 202, 203, etc. to enhance fault tolerance. 7. Example calculations. Single channel, 101. For a single channel system, the PFD calculation is straightforward using the basic principles outlined. Dual channel, 102. For dual channel systems, the PFD calculation involves more complex considerations that account for the possibility of multiple simultaneous failures and their respective rates. 8. Assumptions and limitations. Assumptions. Calculations often assume constant failure rates and perfect diagnostics. Limitations. Real-world conditions may vary, and periodic reviews and updates to the PFD calculations are necessary to maintain accuracy. Conclusion. Accurate determination of PFD is essential for the reliability of safety instrumented systems. The methodology involves understanding failure rates, diagnostic coverage, proof testing, and MTTR, along with applying appropriate principles and considering system configurations. Regular reviews and updates are necessary to ensure ongoing reliability and safety. This detailed methodology provides a comprehensive guide for engineers and safety professionals to calculate and maintain the PFD of logic solvers in SIS, ensuring the continued safety and reliability of industrial processes. SIL evaluation techniques as per ISA 84. Introduction to SIL evaluation. Safety integrity level evaluation techniques are essential for ensuring the reliability and safety of safety instrumented systems SIS. These techniques help determine whether SIS meets the required SIL for specified safety functions, which is critical for process safety in industrial applications. Calculation of probability of failure on demand, PFD. Understanding failure rates. Failure rate. The failure rate of each component involved in the SIS must be determined. This includes both dangerous and safe failures. Dangerous undetected failures, later DU. Failures that do not get detected by diagnostic tests and can cause the S to fail on demand. Safe detected failures, DX or SD. Failures that are safely detected and do not lead to a system failure on demand. Diagnostic coverage. Diagnostic coverage, DC. The effectiveness of diagnostics in detecting failures. It is expressed as a percentage and calculated based on the ratio of detected failures to the total failures. Proof testing. Proof test interval, TI. The time interval between manual tests that verify the SIS is functioning correctly. This interval greatly affects the PFD calculation. Proof test coverage, PTC. The effectiveness of proof tests in revealing undetected failures. Mean time to restore, MTTR. Mean time to restore, the average time taken to restore the SIS to its operational state after a failure has been detected. This includes repair time and any delay in initiating repairs. Redundancy and voting configurations. Redundancy, using multiple components to perform the same function to improve reliability. Voting configurations. Systems can be configured in various voting logics, like 101, 102, 202, 203, etc., to enhance fault tolerance. Example calculations. Single channel 101. For a single channel system, the PFDFG calculation is straightforward using the basic principles outlined. Dual channel 102. For dual channel systems, the PFDFG calculation involves more complex considerations that account for the possibility of multiple simultaneous failures and their respective rates. Assumptions and limitations. Assumptions. Calculations often assume constant failure rates and perfect diagnostics. Limitations. Real-world conditions may vary, and periodic reviews and updates to the PFD calculations are necessary to maintain accuracy. Conclusion. Accurate determination of PFD is essential for the reliability of safety instrumented systems. The methodology involves understanding failure rates, diagnostic coverage, proof testing, and MTTR, along with applying appropriate principles and considering system configurations. Regular reviews and updates are necessary to ensure ongoing reliability and safety. This detailed methodology provides a comprehensive guide for engineers and safety professionals to calculate and maintain the PFD of logic solvers in SIS, ensuring the continued safety and reliability of industrial processes. SIL evaluation techniques as per ISA TR84.02. Modeling of SIS element failures. The objective of this section is to define the terminology and symbols for the different types of SIS element failures to be used by the safety integrity evaluation techniques that are discussed in the following sections. The SIS elements include input field devices, sensors, arithmetic logic solvers, and output field devices, final elements. Electrical E, electronic E, and programmable electronic PE technology elements are modeled for the arithmetic logic solver functions. Failures are grouped into two major categories. 1. Physical failures. Independent failures. These occur when some physical stress or combination of stressors exceeds the capability of the installed components. Common cause failures. These occur when multiple failures happen simultaneously due to a shared root cause, such as radio frequency interference. 2. Systematic failures. These occur when the physical hardware is operating but unable to perform the specified function due to errors of omission or commission. Systematic failures are further classified into safe failures, let SF, result in a spurious trip. Dangerous failures, result in a fail-to-function state. Partitioning of SIS element failures. SIS element failures are partitioned into safe failures and dangerous failures. Failures causing the SIS to shut down the process without a process demand present are categorized as safe. Failures causing the SIS to fail to respond to a process demand are categorized as dangerous. Safe failures, denoted by the superscript S. Dangerous failures, denoted by the superscript D. Failures are further classified based on their detection status. Safe detected, see safe undetected, SU. Dangerous detected, dangerous undetected. # modeling of field devices. 1. Modeling of sensors, input field devices. Sensors interface to the SIS through analog input boards, digital input boards, and serial communication links. Sensor failure rates are split into 4 mutually exclusive categories: safe detected, DS, safe undetected, less US, dangerous detected, dangerous undetected, US. 2. Modeling of final elements, output field devices. Final elements interface to the SIS through analog output boards, digital output boards, and serial communication links. Final element failure rates are split into 4 mutually exclusive categories: safe detected, SDA, safe undetected, dangerous detected, dangerous undetected. Modeling of elements in PES arithmetic logic solvers. Programmable electronic systems, PES, can vary significantly in architecture. Typical architectures include 1. Small single-board PES with integral I/O. 2. Multi-board PES with main processor module and processor-based I/O modules. 3. Multi-board PES with main processor module and I/O chassis with I/O processor module and non-intelligent I/O modules. System modeling. System modeling of any fault-tolerant EEPES architecture can be done using simplified equations, fault tree analysis, Markov models, or other techniques using the failure rate categories described above. Accurate and detailed failure modes effects and diagnostic analysis, FMEA, is essential for this classification. Failure rate data for commonly used field instrumentation. To predict the MTTF spurious and PFDAG of a SIS, failure rate data of different components such as sensors, logic solvers, and final elements are required. This data can come from various sources such as public databases, user-compiled maintenance records, vendor-compiled field returns, reliability calculations, or operating experience. This section outlines the fundamental principles and methodologies for modeling SIS element failures, critical for conducting accurate SIL evaluations and ensuring the safety and reliability of industrial processes. Determination of SIL by Markov analysis as per ISA TR84.02. Section 4. Introduction to Markov. The Markov approach, or Markov modeling technique, originated from the Russian mathematician A.A. Markov. The basic principle of Markov analysis is that a system can exist in different states defined by internal failures. These states are often driven by the availability of data, which can be at various levels of detail. The states are typically classified as fully operational, partially failed, degraded but still functional, or totally failed. A Markov model consists of states and transitions between these states, driven by the failure or repair probability of components. Transitions can occur due to a component failing or being repaired. Section 5. Modeling and calculation procedures. The Markov approach offers flexibility in modeling different aspects important for SISs, such as failure modes, repair strategies, diagnostics capabilities, and common cause or systematic failures. However, it also comes with computational and modeling complexity. The following steps outline the procedure for modeling and calculating SIL using the Markov approach. 1. Assign safety functions. Each safety function is assigned to its SIS as defined in the safety requirements specification. 2. List components. List all components that have a safety impact on each safety function, including logic solvers, sensors, and final control elements. 3. Identify failure modes. List the possible failure modes for each component. 4. Determine system states. Identify degraded, intermediate, and failure system states by systematically introducing different failure modes of each component and their effect on the safety function. Construct the Markov model by determining how the SIS can be repaired from these states. 5. Solve the Markov model. Determine the probability of being in any state as a function of time. 6. Calculate PFDAG and spurious trip probability. Calculate the average probability of failure on demand and the probability of a spurious trip of the SIS. 7. Verify SIL requirements. Ensure the PFDAG of the S meets the SIL requirements of the Safety Integrity Requirements specification. 8. Modify configuration if needed. If necessary, modify the configuration, hardware configuration, functional test interval, hardware selection, etc., and repeat the process from step 3. 9. Adjust for spurious trip probability. If the calculated probability of a spurious trip is unacceptable, modify the configuration, incorporate redundancy, use more reliable components, etc., and repeat from step 3. 10. Finalize calculation. Once the SIL and the probability of a spurious trip meet the specified requirements, the calculation procedure is complete. Have assumptions in Markov modeling. 1. Component failure and repair rates are constant over the life of the SIS. 2. Redundant components have the same failure rates. 3. Sensor failure rates include everything from the sensor to the input module of the PE logic solver, including process effects. 4. Logic solver failure rates include input modules, logic solvers, and output modules. 5. Final element failure rates include everything from the output module to the final control element, including process effects. 6. Once a component has failed in one of the possible failure modes, it cannot fail again until it has been repaired. 7. Fail-safe and fail-dangerous states are treated as absorbing states, meaning they are not repaired to simplify the modeling effort. 8. Systematic failures are neglected. 9. The evaluation time equals the functional test interval or mission time, typically 1 year. 10. Power supplies are not considered in the first two examples. 11. The beta model is used to treat possible common cause failures. Examples overview. Example 1. Safety instrumented system with 2 sets of sensors, each capable of shutting down the process without diagnostics. Example 2. Similar to Example 1, but with diagnostic capabilities for sensors and valves. Example 3. Highlights additional features like periodic and imperfect testing. Base example, common example across parts of TR84.02, demonstrating the procedure and technique for calculating SIS PFD AG and MTTF spurious. The Markov analysis technique provides a comprehensive method for evaluating the reliability and safety integrity of safety instrumented systems, accommodating various failure modes, repair strategies, and diagnostic capabilities. SIL evaluation by fault tree analysis as per ISA TR84.02. Introduction to fault tree analysis. Fault tree analysis, FTA, is a structured graphical technique used to analyze the probability of system failures. It examines the interlock or the interaction of multiple interlocks within a safety instrumented system, SIS. Originating in the 1960s at Bell Telephone Laboratories, FTA has evolved to be widely used in various industries, including the process industry, to evaluate potential failures in safety systems. FTA uses a top-down approach, beginning with a top event that represents a system failure. The analysis then identifies all possible causes leading to this top event. It employs logical symbols and gates to depict these relationships, ensuring a comprehensive analysis of potential failure pathways. Warnings. 1. FTA cannot account for all possible failure pathways and relies on the analyst's identification of these paths. 2. It is not a substitute for good engineering design principles, but a tool to assess the SIL of the SIS design. 3. Different methodologies like FTA and Markov modeling may yield different results due to their inherent mathematical approaches. Assumptions for fault tree calculations for an SIS. Several key assumptions are made when using FTA for SIS evaluations. The SIS is designed, installed, and maintained per ANSI ISA S84.1-1996. Component failure rates are constant over the system's life. Component failures are statistically independent, although dependent failures can be modeled. Once failed, a component remains in that state until repaired. Testing is assumed to be perfect, detecting all covert failures. Repairs restore components to their normal state, with imperfect maintenance considered for higher SIL applications. Testing frequencies are higher than failure rates. The reader is familiar with FTA techniques and principles. The FTA process for SIS involves several key steps. 1. SIS description and application information. Gather detailed information about the CS architecture, instrumentation, process description, support systems, testing frequency, failure modes, diagnostic coverage, repair intervals, maintenance procedures, common cause failures, and systematic failures. 2. Top event identification. Define the top event for SIL determination, representing the probability of the SIS failing on demand for a given safety function. Multiple safety functions may require separate fault trees. Construction of the fault tree. Construct fault trees using appropriate failure logic, starting from the top event and identifying all basic events that could lead to this top event. Include primary, common cause, and systematic failures. 4. Qualitative review of the fault tree structure. Review the fault tree with process and instrumentation designers, operations, and risk assessment teams to ensure all significant pathways to failure are captured. 5. Quantitative evaluation of fault tree. Use failure rate data to quantify the fault tree. This involves using Boolean algebra to calculate the PFD and the MTTF spurious. Conservative failure rates should be used for SIS components to ensure a higher estimate of PFD. Generate a cut set report to identify critical failure pathways. 6. Documentation of FTA results. Document the SIS application, assumptions, reference documents, data, model, cut sets, PFD, MTTF spurious, sensitivity studies, and recommendations for SIS improvement. This procedure ensures a comprehensive evaluation of the SIS, helping to identify weaknesses and improve system design to achieve the required SIL. The documentation provides a detailed record of the analysis, supporting ongoing safety and reliability efforts. Comparison of Markov analysis and fault tree analysis for SIL determination. Both Markov analysis and fault tree analysis, FTA, are established methodologies for evaluating the safety integrity level, SIL, of Safety Instrumented Systems SIS. Each method has its own set of advantages and disadvantages, making them suitable for different applications and contexts within SS evaluation. Markov analysis. Advantages. 1. State-based modeling. Markov analysis excels in modeling systems with multiple states, including operational, degraded, and failed states, providing a detailed representation of the system behavior over time. 2. Time dependency. It explicitly includes time as a parameter, allowing for the modeling of dynamic aspects such as maintenance and repair activities. 3. Maintenance and repair. It can model various maintenance strategies and their impact on system reliability, accounting for both perfect and imperfect maintenance. 4. Diagnostic coverage. Markov models can effectively incorporate diagnostic coverage in periodic testing, providing a realistic assessment of the system's performance. 5. Complex systems. Suitable for complex systems with interdependent components and multiple failure modes, as it can handle the dependencies and transitions between different states. Disadvantages. 1. Complexity. Markov models can become mathematically and computationally complex, especially for large systems with numerous states and transitions. 2. Data intensive. Requires detailed failure rate data, transition probabilities, and repair rates for all components, which can be challenging to obtain. 3. Tool dependency. Often necessitates specialized software tools for accurate modeling and analysis, which may not be readily available or easy to use. Fault tree analysis. Advantages. Structured graphical representation. FTA provides a clear and intuitive graphical representation of the failure logic, making it easier to visualize and understand the system's failure pathways. 2. Component-level analysis. It allows for a detailed analysis of individual components and their contributions to the overall system failure, facilitating targeted improvements. Minimal cut sets. Identification of minimal cut sets helps in pinpointing critical failure combinations that significantly impact system reliability. 4. Widely accepted. FTA is a well-established and widely accepted method in various industries, supported by extensive literature and standardized symbols. 5. Qualitative and quantitative analysis. It combines both qualitative and quantitative aspects, allowing for a comprehensive assessment of the system's reliability. Disadvantages. 1. Static nature. FTA is generally static and does not explicitly account for time-dependent factors such as maintenance and repair activities. 2. Complex fault trees. For large and complex systems, the fault trees can become very large and difficult to manage, potentially obscuring critical failure paths. 3. Assumptions on independence. FTA often assumes the independence of component failures, which may not always be realistic, especially in systems with common cause failures. 4. Limited dynamic modeling. It is less effective in modeling dynamic aspects of such as changes in failure rates over time or the impact of different maintenance strategies. Summary. Markov analysis is more suitable for dynamic, state-based modeling of systems where time-dependent factors and complex maintenance strategies are critical. It provides a detailed and realistic assessment of the system's behavior, but at the cost of increased complexity and data requirements. Fault tree analysis, FTA, offers a clear and structured method for identifying and analyzing failure pathways, making it easier to understand and communicate the system's reliability issues. It is well suited for systems where a static analysis is sufficient and is widely accepted in various industries. However, it may struggle with dynamic factors and large, complex systems. In practice, the choice between Markov analysis and FTA will depend on the specific requirements of the SIS evaluation, including the complexity of the system, the availability of data, and the need to account for dynamic factors. Often, a combination of both methods can provide a more comprehensive assessment, leveraging the strengths of each approach.